Okay, so here we go. This is where life gets really nice, really fast. So here's another system. Again, we could solve this with inverse matrices like we learned to do just a few minutes ago. But I want to show you another way of doing it using what's called augmented matrices. And usually, for most people, they like augmented matrices much better. So first, I'm going to represent this as a single augmented matrix. And all an augmented matrix means is put all the numbers in it. So I'm just going to put everything together. Thus. Right? It's the coefficient matrix with an extra column added on for the solutions that I want. In a normal pre-calculus class, what you do from here is you learn something called Gauss-Jordan elimination, which is a very labor-intensive, handwriting-intensive process. I want to sketch the outline of that for you because they'll ask you about it. They won't ask you to do it, but they would ask you what makes sense to do first, and then you would move on from there. So what Gauss-Jordan elimination does, plus it's just a great name. The idea is that just like elimination, right, when we did the simple elimination stuff, we were just trying to knock out variables by multiplying an equation by something and then adding. It's the same thing here, where I can just, what I'm allowed to do is multiply a row by any number that I want, then add it to any other row. And so I'm allowed to take, not take, bad word, multiply a row by whatever I want, and add it to any other row. And my goal in this is to get everything zeros except this diagonal. When I reduce this matrix to this, then I know the answer to my system is just x equals a, y equals b, z equals c. So I basically changed these three terrible equations into just the equation 1x equals a, 1y equals b, 1z equals c. It's a really nifty way to do a bunch of elimination at once, but it's very time consuming when you do it by hand. So, for instance, well, one other thing that I can do, I can also switch rows, right, because this order is totally random. So what you see a lot is you see like, okay, here's my original. And I say, all right, I want a 1 up there, so I'm going to switch those two rows. And then you say, all right, I want a 0 there, so I'm going to multiply this guy by -2 and add. So 1 times -2 is -2. Added to 2 is 0. Times -2 is 2. Added to 1 is 3. Times -2 is -2. Added to -1 is -3. Times -2 is -4. Added to 4 is 0. And you keep going, keep going, keep going until you get this. It's a grind.
Wait, can you explain that one more time?
So, oh, this step?
Well, yeah, like how'd you get the top one's the original one, right?
Right. Top one's the original.
So then how'd you get the second one?
I just switched those two rows because, right, I don't care what order these are in. I could have just easily written this is the first equation and this is the second equation.
Okay.
So I'm allowed to flip whatever rows I want.
And so you knew you already had the one.
Right, so I have the one, so I'm just going to put that guy up there. That solved that problem. And then here, I know I wanted a 0 underneath the 1. So I realized, oh, if I multiply this by -2 and add, that'll make that 0. So I multiplied this whole row by -2 and added it to that. And that got me my 0, where I wanted a 0. And technically, what you would then do to go through the whole Gauss-Jordan elimination is you would keep doing that process until you got exactly this matrix in about 7 steps from now. There is one. I just want this to sink in, the idea of it. The idea is that we're just multiplying rows by numbers and then adding. And that what this does is it's getting us closer and closer to x equals that, y equals that, z equals that. Now this is a very mechanical process, a mindless mechanical process, and that's what calculators love to do for us until they rise against us for having to do these terrible things all the time. But we do have a shortcut on this. And it's actually all you have to do is you just enter this matrix into your calculator, and then under that Math tab, you have this button called RF. So this stands for Row Reduced Echelon Form. And what that does is it will take any matrix and reduce it down as far as it can go. So try that out. Enter this matrix in as matrix A, and then under the Math tab of your matrix,
it's down at the bottom.
well, it also has a number short jump that you can jump straight to it.
B.
Oh, yeah, that's good and inconvenient.
Alpha apps.
So
So doing 3 by 3.
or you could do 9 and then go down.
So try RFA, and what you'll discover is that in about half a second, it does all this stuff. Yeah, exactly. There you go. So yeah, this is a 3 by 4 matrix.
I didn't even plug in the matrix. What is it?
So your A matrix is this guy.
Do not touch. Oh.
And what you should do, once you RF that, this is what you should end up getting. Now, ref.
Isn't
RF.
there a ref?
There is a ref that doesn't row reduce. It gets it down. It'll get you these zeros, but it'll leave these alone. So,
Why'd you want that?
there are applications where that's useful, but for us, we're going RF all the way. So there's a couple of weird things that can happen when you RF. But generally speaking, any time that you have a system of equations from here on out, you can use RF on it, and that's the loudest rapper I've ever heard. So if you get this and just this, exactly kind of like that, 100010001, and all numbers there, you know that there's a solution that exists, and that that's the solution. If there's no solution, it will either yell at you and say, why? Or it'll look something like this. It'll give you something which is absurd, which this equation says that 0 equals 4. So if you ever have all zeros and then a number as a row, you know that there's no solution. Not a 4 and a number. Otherwise you're going to think it's just a 4. right, the bottom line is a nonsense equation, which is technically the row reduced echelon form of it. They've reduced it down as far as they can go, but actually they could reduce this down to a 1 even further. But yeah, anytime you see that, there's no solution, and that's your calculator's way of telling you. Multiple solutions is whenever you have a row of just zeros. So you might have 1, 0, 1, 5, 1, 2, 6. What this is telling you is that these three planes don't just meet in a point, they meet in a line. So there is actually an infinite number of solutions. So when I have this thing happening, all zeros and then numbers here, this is saying solution is a whole line worth of points. Given by the first couple of ones. I don't answer for these two guys actually describing anything. I put in random numbers. But the idea is if you get a full line of zeros on the bottom and you see that it's not 1, 0, 0 something, but 1, 0 number something, it's trying to tell you there's more than one solution to this system. Most of the time it'll be like this, but every once in a while there'll be jerks. It'll be either this case or this case. Yeah.
For both those cases, does it have to be the bottom row?
It'll put it as the bottom row,
Okay.
as part of the RFing process.
Okay.
Yeah, the calculators are smart like that. Super smart. Okay. And that's pretty much what there is to say about matrices, as far as you guys are concerned. There's a whole world more to say about matrices. And once you get into the branch of math called numerical analysis, you can actually use matrices to solve calculus problems for which there is no solution possible in the realm of normal calculus, but you can still solve them with brilliant approximation methods. It is a fantastic branch of math, which I heartily recommend all of you in your careers as mathematicians take. So what that leaves us with now is a slightly less elegant world of systems of inequalities. This is very graphing intensive. And not necessarily calculator graphing intensive, because those get a little bit muddy, but it's oftentimes very hand graphing intensive. So the idea here is, well, let's say that instead of a system of equations where we're looking for where they meet, what this does is it basically borders in a part of the xy plane, and it says in this little area, all of these inequalities are met. Right? In this little area lie all the possible solutions to this system of inequalities. So the answer is not a point, it's an area. So for example, let's say I had this simple system. The system x is greater than or equal to 2, and y is less than 2. Well, the set of all numbers who have an x value greater than or equal to 2, this is the line x equals 2, And if I want to be greater than or equal to 2, I want everything on that side of that line. So I want everything that direction. Let's use red. For a while. If I want all the numbers y less than 2, well, here's the line y equals 2. I'm drawing a dashed line since I don't want to include y equals 2. And I want everything less than that 2 value. So I want everything less than 2. And so the solution to this system of inequalities, the set of all values, all points, which are both have an x value greater than or equal to 2 and a y value less than 2, is the one where both of these are met. Everything on this side of that line and that side of that line. So in other words, that area in there. Any point in there satisfies both of these inequalities. That's the idea of a system of inequalities. It gives you a nice little area where you pick any point in there, and the x and y values at that point satisfy all the inequalities that I give you. The first thing that you're going to want to do when presented with a system of inequalities is graph the lines. Graph the equalities. Alright, we use solid lines whenever there's an equal sign, and I use dashy lines whenever there isn't. Alright, the dashed line says don't include the stuff on the line. 2, figure out which side is shaded. By plugging in a test point. Three, fill in the overlap of all shaded regions. So it's those 3 steps. Graph the lines, figure out which side to shade, that's where my little arrows come in, and then fill in the part of the graph where all the arrows are pointing towards. If you do that, you can't go too far wrong, as long as you remember how to graph lines. So let's try a slightly more interesting example. By interesting, of course, very hard. So let's say I've got y is less than or equal to x plus 2. X is less than or equal to 4. And y is greater than or equal to negative 2. Okay. So solving that system is finding that area where all 3 of those conditions are met. Some of you might be wondering to yourselves, where on earth is this possibly useful? Actually, more places than you'd think. Because usually what each one of these are is an economics, business, or something like that, is it represents a constraining factor. That, for instance, I can't make any more than 4 million trucks or Kardashian dolls or whatever. And I can't pay my workers any less than negative $2 per hour. what, how many Kardashian doll trucks can I make?
Don't you
Given-
find like the corners of the thing?
Exactly. So what you do is, this is great for optimizing systems of constraints, which is what you're doing all the time when you're trying to run factories and stuff. Is that, how do I not overproduce? Where should all of my efforts go in order to make the most amount of money possible? Or generate the most amount of love possible, or whatever you're trying to optimize. So if I've got this guy, I'm just going to graph the line y equals x plus 2. He's got a y-intercept of 2 and a slope of 1. So that's that line. And I want to be y to be less than or equal to x plus 2. So I'm going to test the origin here. If I put 0, 0 in, is 0 less than or equal to 2? Yep. So that side's the side that I want. Since that point worked, everything on that side of that line will work.
Crazy. That's crazy, man.
Okay, x is less than or equal to 4. So here's the line x equals 4, roughly. I want to be less than or equal to 4, so I want that side. And y is greater than or equal to negative 2. Here's negative 2. And I want to be greater than that, so I want to be above. So the region that describes these three inequalities is the region where all the arrows are pointing. And as you can see, that's directly in the middle here. Anything in that zone within that triangle will fulfill all three of these requirements.
Yes. So this is used for like optimizing, right? Like
Yeah.
But with it, is there like only two products? Like I remember like the examples we did last year were like
Yeah.
you had two types of products that some manufacturer had to make.
Uh-huh.
So how would you do like three products?
If you were trying to do 3 products or 4 products, then you're dealing in a greater dimensional space, which you would use matrices to deal with, basically. There's some really cool things that you can do with those, but which are totally outside of what you're going to be asked to do here. Okay. So, since we just talked about it, well, actually, let's wait for optimization until we make sure everybody can sort of get these down. So try graphing that system. Actually, let me make this a little easier. This will get so you don't have to go quite so low.
Thanks.
X is less than or equal to 2. Hopefully you got something that looks like this. Looks like most of you did. Where you graph this guy. Hey, it hit. I'm going to test 0, 0. Is 0 greater than negative 2? It is. So I want that side. I'm going to graph y is 4. I want to be less than that. And I'll graph x is less than 2. Eh. So it should look like that. With the center bit. Shade. So, trying to preserve my markers.
Only one shade.
Oh, the
One shade
shade,
of
the shade of it all. So that's how that works. And now, to do optimization problems, which is our last topic for the day, all you have to do is do that and then find the corners. So find the corners of the shaded zone.
If you had used the inequalities and only a gray marker, would you end up with an adult novel?
So,
M_N_PM_N. It's confusing.
so what optimization problems are all about is, so optimization problems are all about taking a group of constraints, which could be a group of, this is how much it costs to make this product, this is how popular it is, this is our capacity for the factories, this is how many workers we can afford to off every week. All little constraints like that. How many orphans we can offer up and sacrifice every week to make this product. Little things like that. You put them all together and you're trying to find out like when your maximum profit is, or when your minimum cost is, or what your maximum happiness is, or something like that. So how to do this is you're going to be presented with a series of constraints. Which are the inequalities. And you'll have an equation to optimize. So it'll be really easy to tell which one's which, because one of them will have a bunch of inequalities, and the other one will have an equal sign. Right? So you can always tell pretty easily which one's which. So your course of action is to graph the system of inequalities, just like we did here. And then 2, find the corners. That's the most important part of this whole thing, because it's a fact that the optimized values of any of these equations that you're going to get are to be found at the corners. It's not going to be found somewhere in the middle, it's going to be found at somewhere at one of those extreme corners. So you're going to have to find the coordinates of those corners, and then 3, plug the corners into the equation.
See which one is the biggest.
Or yeah, biggest or smallest. So let's say that we've got this system. I want to, this is just the system that we used in the last equation, the last system, so you can reuse that graph. And I want to find the maximum value of this function, 3x minus 2y. I call it p, let's say it's a profit function of some sort. I want to maximize profit in this little area with those constraints. So what I've got to do is I've already graphed it. Step 1 you've already done. Step 2, I need to find the corners. That's this guy, and that guy. One of them's pretty easy. This one is at 2, 4. Whenever I've got horizontal lines meeting vertical lines, those are easy corners to find. The other ones, however, I'm going to have to set equations equal to each other. So let's call this guy A, B, and C. So B was easy, but A, I need to find where the line y equals 4 intercepts the line y equals negative 2x minus 2. I need to find where those two lines intersect. So I'll just set them equal to each other. So I get x equals -3, and of course y equals 4 because it's the line y equals 4. So that's A. And then C, I just need to find where the line x equals 2 meets the line y equals -2x minus 2. Where do those two guys meet? Well, they meet where x equals 2. So that's what I'm going to plug in here. So point C is at 2, -6. So those are my 3 corner points. And now I just have to see which one of those 3 optimizes this equation, which one maximizes it. So step 3, I'm going to plug each one of those into my profit equation. So point A was -3, 4. -17. If I plug in point B, where'd it go? Point B. I get -2. And if I plug in point C, 2, -6. I get 18. So A gives me my minimum for that function, and C gives me my maximum for that function. So this is my optimum value. If they ask you for your maximum value, it's the one you get when you plug into the equation. If they ask what are the coordinates that give you your maximum value, that would be my 2, -6. So this is the most labor-intensive thing you're going to have to do. Pretty much all the rest of this chapter is calculator work, being able to be very swift and free with your matrix operations. This one, though, is entirely grease work. You just gotta go through it and go through it and go through it. You can save yourself a little bit of work by graphing all the equations on your grapher and seeing, and then you can find the points of intersection using your intersect feature. So that'll save you some time on step 2. The only problem is that most graphers have a little bit of an issue graphing vertical lines.
That seems like it should be the easiest.
See, you'd think, but to get them to do it, it's...
But would you do it without inequalities then?
Well, if you have an 84, you're going to be doing it without inequalities. You'll just graph the equalities and sort of know that the part that you're interested in is the center part. 89 and Inspire, I think, can graph them as inequalities. So it will actually show you where the center is, as I recall. So, yeah.
When do we need to know that it's a center part?
Well, generally speaking, if it's an optimization problem, it's got to be the center zone that's cut out by all those different guys, because otherwise you don't have corners. If it were like this part, then optimizing it would be x equals infinity and y equals negative infinity or something like that. So it's going to be the part that has the boundaries rather than the parts that are unbounded over here and over here and over here. That's just how they work the questions usually. That's not the case universally, but for these sorts of questions, it's 95% of the time going to be the center of it.